We will start with the Fermi-Dirac distribution itself. We know that the Fermi-Dirac distribution for electrons.
Please keep your mic properly, sir.
Isn't it audible?
Sir, किसी टाइम स्लो आता है, किसी टाइम हाई आता है.
Okay, now?
Yeah, sir. Now okay.
Okay, it's fine. So if this is the we are required to find the probability, and we will use the Fermi-Dirac distribution for some energy level E, and it is given by 1 plus exponential of E minus EF.
What is the question is asking? I am not understand.
Okay. In question, it is asking us to find the Fermi level, where the Fermi level lies, and we are given the conditions on the probability of this occupation of electrons and the occupation of holes, and it is given that these two probabilities are equal. So, did you got the question?
Yes, sir. Yes, sir. Yes, sir.
Okay. Then, if we write it like this, this Fermi-Dirac distribution, that the probability of a state which is being filled by an electron at some energy level E, it's given by this Fermi-Dirac distribution, and for holes, it is simply the 1 minus this thing, and it will become exponential of EF minus E by KT. Now, in this question, we have been given that these two conditions for some energy level.
In formula, this is EC or EV? You direct.
This actually is, this formula is valid for some particular energy level. In here, it's just some energy level, E. Here we are interested. Okay. Now I will put that condition, because we have been given that this energy level, these two probabilities are equal for EC minus KT and EC minus 3KT for the hole and the electrons. So we will equate these. We will write that this EE, where this is the electron energy, is EC minus KT, and for holes it's EC minus 3KT. EC minus 3KT. So if we equate these two as it's given in the Hello?
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 Hello? Yes, sir.
Hello?
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 Yes, sir. Can somebody confirm whether I'm audible or not?
Yes, sir. You are audible.
Hello?
Hello? Hello? Yes,
Hello?
sir. You are audible.
You can put it in the chat. Okay, thank you very much. Let me share the screen again. So, what we were doing, somebody is knocking. Okay, wait a minute. So, we were equating these two Fermi-Dirac distributions, and we will be simply getting 1 plus exponential of EC minus KT minus EF by KT equals 1 plus exponential of EF minus E minus EC minus EC plus 3KT divided by KT. This 1 and 1 will go, 1 and 1 will go, and we will be left with the exponentials only, and we will take ln on the both sides. If we take ln on both sides, we will simply equate these two. It will be EF minus EC plus 3KT is equal to EF minus EC minus KT. It will be EC minus EF minus KT. So simply it will become 2 times, if we take EF on the other side and EC on the other side, it will simply become 2 times EF is equal to 2 times EC minus 4 KT. Yes, minus 4 KT. And if we divide by 2, it will simply be EF is equal to EC minus 2 KT. So we have been able to locate the Fermi level. Fermi level. So the Fermi level is at is 2 kT below the conduction band. And now let's check our options. And for this, it is below the 2 kT below the conduction band, and option B seems to be the correct one. So we will go with option B. Now let's move to the another problem where it states that we have a silicon wafer which is doped with arsenic atoms, and the doping concentration is of the order of 10 to the power of 16 per centimeter cube, and the donor level lies below the conduction band, and the distance between the two is 54 millielectron volts. Now we are required to find the percentage of donor atoms that are ionized at some temperature that is given to be 77 Kelvin, and we have been given effective density of states Nc for that temperature as well, and we have been given the degeneracy factor is for this donor level to be equal to 2. Now we will use first the charge neutrality condition. We know, as taught by the professor, the charge neutrality is given by P plus Nd plus is equal to N plus Na minus. That is, we now know for this small temperature because this intrinsic current concentration will be very less. So we can neglect it. Now, also, we can write
Hello.
this Nd positive to be equal to N. So we know this N, this electron concentration is as derived in the graph is given by Nc exponential of Ef minus Ec by kT. So if anyone has any question, he can put it in the chat window. Let me check the chat window if it's possible. I thought that someone might be speaking, so there's no question. If you have any question, you can put it in the chat window, and I will check it after the completion of this question, because I have to go back to this Google Meet again and again to check. So let me solve this question first, and after that I will take the question which if there is any in the chat window. So this electron concentration will simply given by this expression, this Nc Ef minus Ec by kT, where this Nc is the effective density of states. Now also we know that this ionized donor concentration, this donor concentration is given. It is given by Nd positive is equal to Nd divided by 1 plus Gd, where this Gd is the degeneracy factor, Ef minus Ed by kT. So we have now also another condition on this Nd. So we will be simply writing this Nd positive. If we use now this condition, this N will be equal to Nd divided by 1 plus Gd exponential of Ef minus Ed by kT. That's simple. Now we will try to do some manipulations and try to get it in this form, this equation, so that we will get N in the denominator as well. So if we do some wise manipulations, we will be getting Nd 1 plus Gd exponential of what we will be doing, Ef minus Ec by kT, and exponential of Ec minus Ed by kT. What we have done in here is we have simply added and subtracted the conduction band edge Ec to the to this over here, to this expression over here, and we have split this into 2 now. Now we have split this exponential into 2 now, and now we will try to get some relation with this thing over here, so that we can get some relation for this effective electron concentration. Now we know that now this N by Nc, this N by Nc will be given by this exponential of Ef minus Ec by kT. So this N by Nc will be this thing, Ef minus Ec by kT. So we will be left with Nc, N is equal to Nd 1 plus Gd N by Nc into exponential of Ec minus Ed by kT. Yes, as that simple. Now we need to solve this equation, and we can clearly see that this expression over here, will be quadratic in N. So let us do another wise manipulation by saying that this expression over here, it's substituting it to some value. so that we are easy to go with in our next processes. So we will say that let some variable x be equal to nc. This variable is equal to nc by gd, exponential of minus ec minus ed by kt. Yes, exponential of minus of ec minus ed by kt, as that simple. Now, if we put this x in the previous expression, it will simply be n is equal to nd, n is equal to nd divided by 1 plus n by x. Now, this n will simply be equal to n plus n squared by x equal to nd, or simply this n square plus nx minus nd will equal to be 0. Now, this is simply some quadratic equation in n which need to be solved, and we will be solving it by saying that n is equal to minus x plus times x square plus times 4x and d. That's simple, divided by 2. What we have done in here is we have simply solved this quadratic equation. Now, this x, we need to solve for this x, and it may be if we solve it for over here, it may solve our time in the preceding calculations. So let's solve this x. For that, we know this kt over here is given at, we need to find the kt at 77 degree Kelvin, because at 300 degree Kelvin, we know this kt is simply equal to 0.026 volts, and in here we can simply solve it for the 77 degree Kelvin by just multiplying the temperature at the 77 degree Kelvin and dividing by the temperature at 300 degree Kelvin. So this will give us the value of kt at 77 degree Kelvin. You could have done other way also. You could have written the value of Boltzmann constant and the temperature and solved separately. But since we know the value of kt for 300 degree Kelvin, it will be much convenient if I do it like this. So this will be divided by 300 degree Kelvin. This is the temperature at 300, temperature of 300 degree Kelvin, and multiplied by 77. So this should give me the value for this kt at, one second, somebody is calling. Thank you. So this will give me the value of this kt to be equal to, let me multiply this, it will simply come out to be equal to 6.67 milli electron volt. This is the value of kt at 77 Kelvin. Now we need to find this value of x, where this x is given by nc by gd, exponential of minus ec minus ed by kt. Now, this nc value, as we know that this was given at 77 degree Kelvin, it is 4.2 into 10 raised to power 18. Now, let me put it over here simply. 4.2 into 10 raised to power 18 divided by this degeneracy factor was given to be equal to 2 for this donor level. This nd is 2, and exponential of minus what it was given, ec minus ed, it was given to be equal to 54 milli electron volts. So let me put it over here, 54 milli electron volts, and the kt at the 77 degree Kelvin, we found it just one step below. It was 6.67 milli electron volt. This milli electron volt and milli electron volt will go, and we will simply need to solve this exponential of minus 54 by 6.67. Let me solve it on the calculator, and it comes out to be equal to into 10 raised power 18 will remain as it is, and it is 3.04 into 10 raised power minus 4, and we have in denominator the 2 factor. So this value of x will simply come out. Let me add some slides. This value of x, if I do the multiplications, it will simply come out to be equal to, x is equal to 6.4 into 10 raised power 14 centimeter cube. Can somebody tell me the units of this x by just looking at this expression? You can put it in the chat window. I can give you 1 minute for this just to think what can be the units of this expression. It will be really great if you can put it in the chat window so that we can have some interaction as well. Let me check the chat window if there's anything. Okay, there is nothing. Arsenic is trivalent or pentavalent. I'm confused. Uh, have, let us discuss it after this. If if nobody is willing to write its units, let me simply solve the question first, and then we will see to this question as put by Sandhya. We will first solve this question. It will simply be centimeter cube, as this NC is having units of centimeter cube, and in exponential, this will be some constant multiplied. This is some number, as in exponential we know this quantity and this quantity over here and this quantity over here as having the same dimensions, and they will cancel out, and we will be multiplying this NC by GD by some number, and this GD is itself some number, and this will be having the units of centimeter cube, which I had put, and nobody wrote it in the chat window. So it's okay. Now if we move, we will solve this quadratic equation. This quadratic equation will simply be equal to now minus x. This is minus x plus x squared is minus 6.4 into 10 raised power 14 plus 6.4 into 10 raised power 14 squared, and this was plus 4 into, and this was 4 into ND, where this ND was given to be equal to, this ND was given to be equal to 10 to the power 16. Okay, 10 to the power 16. So 4 into 6.4 into 10 to the power 14 into 10 to the power 16 divided by 2. Now let me solve this equation on my calculator and check what is the value. So let me put it. So it comes out to be equal to, n is equal to 2.23 into 10 raised power 15 centimeter cube. Now, what we were asked to find is the percentage of the donor atoms that are ionized. Now, we will simply write this percentage to be equal to this percentage of donor atoms. This donor atoms will simply be, that is ionized, donor atoms ionized is simply N by ND, where this ND was given into 100 is 2.23 that we found into 10 raised power 15 divided by 10 raised power 16. Let us check it in the CAD mod calculations, and it will come out to be equal to 22 So we have got to be equal to 22.3%. Now let us check the options, and in here the option C seems to be the correct one. So we have got our answer to be equal to 22.3. Now as somebody had put in the chat, and it is, you can check with the periodic table as well, it is fine, we can find that this is pentavalent. So if we now move to the another question where it states that we have been given that some semiconductor has a density of states which is given by Gc, this expression over here, this Gc in the conduction band, and it is given by some expression Gv, which is some expression in here, and these ARB in these expressions are some constants which are non-zero, and we have been told to assume the Boltzmann distribution. So this can ease our calculations. Now we have been told that we can take this valence band edge EV to be as the reference level. That's, we can take it to be 0, and we have been told that EC is the conduction band energy, and the constant condition is that for the constants we are having that A is equal to 2 times the B. Now we are required to find the intrinsic Fermi level. This question is some good question that will test your understanding, whether you have been able to understand how the professor got to the carrier densities, how the electron density and the hole densities were derived. So let us first write these density of states expressions. This density of state expression for the conduction band is simply A times E minus EC, and for these holes this is GV. This is some really good question. B times EV minus E. So these are the density of states. Now we have to find the concentration. We know if there are some chairs, there will be some probability of occupancy for filling those chairs. That's what professor had taught in the class as well. He had taught us that we have to multiply this density of states with the probability of occupancy, that's the Fermi-Dirac distribution, and integrate it over all the energy levels. That's what we will be doing over here. But in here we have eased our life by just saying in the problem we have been told to assume the Boltzmann approximation, which is that for electrons this Boltzmann approximation is given by, it's just the Fermi-Dirac distribution, but we have neglected the 1 in the numerator, in the denominator. So it simply will become exponential of E minus EF by KT. And for the holes, it will simply be equal to exponential of E minus EF by KT. Now, if I now find the electron concentration, it is simply given by the integral which will start from the conduction band edge and go over till the infinity. This limit, somebody may ask you that why is this limit infinity? Because we know this Fermi-Dirac distribution in here, which is the Boltzmann distribution, this will decay as we go on increasing, as we have seen in the class as well. So it does not matter if we take the limit to be infinity. So it's for the ease of our calculations that we take, and this point is also valid for the generality as well, because we know that there will be no concentration, because we will not be having this probability distribution over the region after some energy. So it will simply be this Gc of E, this is the density, and this is the Fermi distribution, and which in here is the Boltzmann distribution that we have been told to assume. So E minus EC, and this distribution, what we found is the Boltzmann distribution E minus EF by KT dE. So if we now do the voice manipulation again, because we can see that this expression over here is having EC in the limit, and this will simply be equal to E minus EC. Now let me do another voice manipulation by saying that I will be adding the value of EC to this expression, and I'm subtracting the same value so that I can get some expression which look like this. It will help me to ease my integration. So EC minus EF by KT with its limits dE, with its limits between EC to infinity integrated over the energy. Now I need to make some expression look like this. It will simply be A times Fi E minus EC, and this will simply be minus of EC minus EF by KT. What I have done, I have broken this exponential into two and taken the constant part outside the integral. So it will be having the limit EC to infinity, and this will remain as it is E minus EC exponential of minus E minus EC by KT with its integration performed over the energy. So now let me do another manipulation and say that this E minus EC by KT, this E minus EC by KT is equal to some x. This will ease our life. We will get this dE is equal to KT times dx, and also the limits when this E is equal to EC, this x will be equal to 0, and when this is equal to infinity, x will also be equal to infinity. So our limits will now change simply, and we will be having simply the expression to be equal to n is given by A times exponential of, it will be EC minus EF, EF minus EC, EF minus EC by KT with the limits as we have changed it from 0 to infinity now, 0 to infinity, and this A minus E minus EC has been put to be equal to KT times x. This E minus EC will simply be equal to KT times x, and in exponential we will be having minus x, and this dE is given by KT dx. So this will be KT dx. This now, if we take the constants out again, it will simply be equal to A times KT whole squared E exponential of EF minus EC by KT with limits between 0 to infinity x of E minus x dx. Now, you all must be aware of this integral. This is having the limits between 0 to infinity, and we know if some integral looks like this with limits between 0 to infinity, it is simply the gamma integral. In here it is gamma of 2, and gamma of 2 is equal to 1. You can check it with the mathematical books as well, and I think you might have taken some course on the mathematical engineering mathematics, and that exponential
Hello,
of
hello, hello,
EF
sir.
minus EC by KT.
Excuse me, sir.
Lakshmikant, are you saying something?
Yes, sir. Will it not be root over pi?
Actually, audio is not coming. I don't know why. But audio
Hello,
is
sir.
not coming today. Hello.
Hello.
Yeah, you can, Lakshmikant, if you are saying something, please put it in the chat window so that I can check. So I don't think you are saying anything. Let me check the chat again. So if you have any confusion, Lakshmikanta, please put it in the chat. Okay, fine. Thank you, Lakshmikanta. Actually, your audio is not coming. I don't know why. I'm sorry for that. But if you have any question, you can put in the chat window. Uh, I will be really happy to answer. Okay, fine. So let me solve this problem further. For the holes, if I move to the whole concentration, this whole concentration will simply be given where this limit is minus infinity to the convection valence band H, GV, where this GV is the what we have been given, this density of states B times EV minus EC, GV, and where this FH is now the Boltzmann distribution for the holes. And we will simply write this to be equal to, as we know, let me write it down directly, the expression by taking the by adding and subtracting the EV on the both in the exponential term, it will simply be B times EV minus EF by KT. Now the limits are minus infinity to EV, and this GV is having the value of, as we see, this EV minus E. We have written EV minus E exponential of E minus EV by KT dE. Now let us again use the manipulation of do some voice manipulation and say this EV minus E by KT is equal to Y. So now we can simply write the dE to be equal to this minus dE is equal to KT times dy, or this dE is equal to minus KT dy, as simple as that. And the integration limits, as we can see, for the minus infinity, if we put in here the minus infinity, it will simply become the y is equal to infinity. And if we put the E equal to EV, y will become 0. So our integration limits will simply be equal to, if we take the constant term outside, and this will be EV minus EF by KT, 0 to infinity, simple, KT of KT y, EV minus E is equal to KT y, absolutely, and this is exponential of minus y minus KT into dy. So this simply will reduce to the expression of P will be given by B times exponential of EV minus EF by KT, taking the KT square outside and doing the necessary integration, and we will be left with, since I have interchanged the limits, this will become positive, absolutely, and this will be equal to KT 0 to infinity y times EY dy, and this will be equal to B times, this will be having KT square, and this KT square, if we take it outside, it will simply be equal to B times EV minus EF by KT into KT square, and this integral, we know, we solved it previously, its value is equal to 1. So this is simply equal to 1. So we have got some expression for this whole concentration as well, which is B times exponential of EV minus EF by KT into KT square. Now we have been given another condition in the problem. The same problem states that we have to compute the intrinsic Fermi energy at 300 degree Kelvin. So for the intrinsic Fermi condition, we know that this electron and hole concentration, they both have to be equal to same number, that's Ni. So this will simply mean that this EF is equal to EFI, that it is Fermi level is at the intrinsic, it is the intrinsic Fermi level that we are talking about. So if I now put this N which we got in here, this N which we got in here, and this P which we got over here, and if I equate these two, I will get A equal to A multiplied by KT square, okay, exponential of EF minus EC by KT, exponential of EF minus EC by KT is equal to B times exponential of EV minus EF by KT into KT squared. So this KT squared and KT squared will go, and we know this value of A, this value A is equal to 2B. So we can simply say this 2B times exponential of EF minus EC by KT is equal to B times exponential of EV minus EF by KT. So if I add now another slide, so we can see this B and B will go, this B and B will go, and we will be having 2 times exponential of EF minus E on the one side, or what we can do, we can move this 2 on the another side, and we can write it to be equal to exponential of EF minus EC minus EV plus EF. Let me put EF equal to EFI. As we know, this is the intrinsic Fermi level. What I have done, I have divided by this this expression by this EV minus EF by KT, and it will simply be equal to EF minus EC, absolutely, and minus of EV plus EFI by KT. This is equal to 1. 2 times this number is equal to 1. Now let me add these EFIs. This will become 2 times EFI minus of EC plus EV by KT is equal to 1/2. And now let us take ln on both sides. Take ln on both sides. So it will simply become 2 times EFI minus EC plus EV by KT is given by is equal to ln of 1/2. So we now know we now move this KT on this KT expression on the other side, and this EFI will simply be equal to EC plus EV by 2 plus KT by 2 ln of 1/2. But we know one thing, that this EV value, as we have been told to put it equal to 0 in the question itself, we have been told that this is the reference level. So I will simply insert the slide now, and I will write this to be equal to EFI is equal to EC by 2 plus KT by 2 ln of 1 by 2. Now I know this KT by 2 is 0.026 divided by 2 ln of 1 by 2. Let me put it in the calculator and check the values. It will simply come out to be equal to fine. It will simply come out to be equal to EC by 2 minus 9 into 10 raised to the minus 3, which is milli electron volt, which is the value of this EFI, this intrinsic Fermi level. So I have got this value, and now let us check our options. And from the options, what it seems that option A is the correct one. So we have got the solution to this problem, which is a really nice problem. It boosts our concepts. So now since we have completed this assignment 3, now let's move to the assignment 4 today itself. Now in this assignment question number 1, question first, it states that there are 3 scattering mechanisms that are occurring in some semiconductor, and due to, if there is only the first scattering mechanism that's present, then the mobility will be given by 2000 centimeter square per volt second. And if only second mechanism were present, then the mobility would have been given by 1500 centimeter square per volt second. And if only third mechanism were present, then the mobility would have been given by 500 centimeter square per volt second. It is simple that if we use the Matheson's rule, so solution to this problem is using the Matheson's rule. We will simply write the net mobility 1 by mu net. It is simply equal to, since now all the mechanisms are present, now it will simply be equal to 1 by mu 1, 1 by mu 2 plus 1 by mu 3. It will simply be now the even before solving the question, I know the answer will now simply be less than the least mobility that we had got, and the least mobility was 500 centimeter square per volt second. And now I am sure about one thing, that the answer will be less than this value, since I am doing the like this, it's coming out to be in the denominator. So this will simply be 1 by 2000, and this mu 2 is 1500, 1 by 1500 plus this mu 3 is 500, as simple as that. Now let me take this 500 as common factor, and this will simply be 1 by 4 plus 1 by 3 plus 1, and this will be 500 into 4 plus 3 plus 12 divided by 12. And let me add some slide. So this mu net will simply be equal to 500 into 12 divided by 19. Yes, 12% 19. So let us put it in our calculators and check the values. So it will come out to be equal to, approximately it will come out to be equal to 315.7 centimeter square volt second. It will come out to be equal to 316 centimeter square per volt second. So this is the closest integer. So clearly this option A seems to be the correct option for this, as this is the closest to the answer. Now if I move to the second problem, it states that we have to consider a semiconductor which is in thermal equilibrium, and we are having no current. So we have been given some donor concentration, which is some n naught multiplied by the exponential, and we have been given the range over which this expression lies, and this n naught is given to be equal to some constant. Now we have been told to find the value of the electric field that will be present. Now let us simply write our total current equation. We know this total current density J total is simply the summation of two current densities, that is the drift current density and the diffusion current density. Okay, it is the summation of these two. Now if I need to find the total current, I simply need to multiply by the area, since I know I by A is equal to J. So drift, sorry, this will be J drift, into A plus J diffusion into A. So since we have been given this net current is 0, we will equate it to be equal to 0, and we know this is given by drift component is given by Q times mu n, where this mu n is the mobility, into the electron concentration, into E, where this E is the electric field. This is for the drift thing, and for diffusion we are having Q times dn by dx. That's simple. Now we know for this n we have been given expression equal to, n has been given to be equal to n naught exponential of minus 10x. Now if I put this over here, it will simply mean Q times mu n into n naught exponential of minus 10x into E plus Q times dn by dx, which means d by dx of this expression n naught of exponential of minus 10x. It will simply mean that this Q and Q will go, and we will be left with mu n exponential of minus 10x. This was multiplied by n naught into E plus Q, where Q has, I think I have cancelled, yes, Q has gone. This will be at minus 10 times n naught dn. So it will simply be equal to minus 10 times n naught dn exponential of minus 10x is equal to 0. And now this n naught will go, this will go, and we will simply be left with this expression for E is equal to 10 times dn by mu n. But we know this dn by mu n is famous Einstein's relation, and it is equal to kT by Q. So this is simply equal to this E we have been told to find. This E will simply be now equal to this 10 times this value. It will simply be equal to 10 into 0.026, and it will be 0.26 volt per meter. So if we check the options, which option matches, option C is the correct option for this. So option C is what we are going to select. Now let's move to the third problem, And this third problem states that we have been given some electronic concentration that is varying linearly as shown in the figure, and the electron concentration at x equal to 0 is n, and some at x equal to L is 0. So we have been asked to find the total number of electrons that are present in this material, and we have been given this cross-sectional area. Now, if I use some simple mathematics, I will say that the equation of line is given simply by a plus bx, as it's a linear line, and this will be its function. It will look like this. Now I know at x equal to 0 I am having value equal to n. So at x equal to 0 I will be having n. It will mean I have to put this value to be equal to 0, and it will give me n of 0 is equal to a, or a is equal to n. So I have found one constant, and also I have been told that n of x is equal to 0, and I will put this n of x equal to 0. It will mean a plus b into L is equal to 0, or simply b is equal to minus a by L minus a by L, or since a is equal to n, this is equal to minus n by L. So we have found the expression for this, and it is simply equal to n of x is simply equal to a plus bx. A is n, so I take this n common. It will simply be 1 minus x by L, and this is for x less than 0 less than L. Yes, absolutely. Now if I know now this total electrons, these total electrons will simply be now given by the integral. These total electrons will simply, I will integrate it over the space with 1 minus x by L dx, or simply I will be having a times n, where this will be L, this will be L by putting the limits minus x square by 2L, with this having the limits 0 to L, and it will be having a n L minus L square by 2L, L by 2, and it will simply be equal to a n L by 2. So let me check which does it match any option. Yes, it is the option C. So we have got the solution to this problem as well, and it's a n L by 2. So I think it's already 6, and this is enough for today. So let me stop the sharing screen, my screen, and let me ask you if you have any question. Lakshmikanta, I think you are the only one present here. Do you have any question? Let me turn on my video. Okay, Lakshmikanta, thank you very much. So I think you can leave the meeting, and I will also have to leave the meeting. So thank you, Lakshmikanta, for joining. Thank you very much.